The sequential bottleneck is dead. Apple just cut the training time of non-linear recurrent networks from weeks to minutes, using a technique called ParaRNN. While the industry spent a decade abandoning RNNs because they could not scale across GPUs, this ICLR 2026 paper proves that the sequential bottleneck was never a mathematical requirement. By rethinking how we handle recurrent state updates, Apple managed to parallelize the very thing we thought was inherently serial, resulting in a 665 times speedup. This changes the fundamental math of how we train on device models. Why RNNs failed to scale. To understand the fix, you have to look at why we stopped using RNNs in the first place. Transformers dominate because they process an entire sequence at once, while an RNN acts like a relay race, where each token must wait for the hidden state of the previous one. This sequential dependency meant that adding more GPUs did not make training faster. The hardware just sat idle waiting for the next step. Until now, we could only parallelize linear recurrences, which lacked the expressive depth needed for complex reasoning. This leads directly to the core mechanism of the ParaRNN paper. Parallelizing the nonlinear state. The ParaRNN mechanism works by treating the recurrence as a parallel prefix sum problem. Apple researchers developed a custom kernel that decomposes nonlinear state transitions into associative operations. Think of it like a massive tree structure, where the bottom layers compute small chunks of the sequence simultaneously, and the results are combined upwards in log time. This allows the GPU to process thousands of tokens at once without waiting for the final state of the previous token. It is a brute force architectural shift that turns a linear process into a logarithmic one, though it requires specific hardware tiling to avoid memory overflows. The memory and performance ceiling. The benchmarks show that ParaRNN achieves parity with the Llama 3 architecture on standard reasoning tasks while using 90% less memory during inference. Because there is no KV cache to store, a 30 billion parameter model can theoretically run on hardware that previously struggled with 7 billion. However, there is a catch. The paper reveals that for sequences exceeding 32,000 tokens, the associative approximation starts to lose precision compared to standard flash attention. It is a highly efficient solution for mobile devices, but it struggles with the massive context windows that cloud-based transformers currently handle. This performance ceiling suggests a clear divide in where this tech will actually be deployed. The real implication. The return of the RNN via ParaRNN indicates that the industry is moving away from the brute force memory consumption of transformers and toward a more efficient, recurrent architecture for edge computing. By solving the training bottleneck mentioned in the first section and utilizing the parallel scan mechanism we analyzed, Apple is signaling that the future of on-device AI will not rely on massive KV caches that eat up system RAM. For developers and researchers, this means the focus shifts from optimizing attention heads to refining associative state updates. We are likely looking at a bifurcated ecosystem where transformers remain the heavy hitters for massive research clusters, while ParaRNN-style architectures become the standard for anything running on a battery. The real test will be the first production implementation in Core ML, which should reveal if these benchmarks hold up in noisy, real-world applications. Watch for the June developer sessions to see if this architecture replaces the transformer blocks in the next generation of mobile foundation models. Subscribe for more.